With problem number 13, we have an exponential growth problem. But it may not be that simple a problem. And we're asked to tell what is the, which of the, which of the following best describes how the size of the population changes over time. Does it increase without bound? Does it increase for several years and level off? Does it increase for several years and then decrease to zero? Or does it increase and decrease in cycles? So the first thing that I would do with these is I have a mental image in my head of what each of these four different types of increase would look like. For the first one, it increases without bound, which means it just keeps going up. That would be A. B would be a little different. It would increase for several years and then level off. So B might look more like that S shape. C says it increases for several years and then decreases to zero. So C might look more like that. And D says it increases and decreases in cycles. So D might look something like that. So here are your four choices. So basically we have to find out what's going to happen here. Now we could obviously just plug this into the calculator and look at what happens over time. However, these are big numbers here, and so not only is it a complex function to enter into my calculator, but it's also going to be difficult to find the correct viewing window within the calculator for that. So that is an option. I'll do that in a second, in a bit, but you may just want to think about what's happening here. Now the only thing that's really changing in this is the piece that goes e to the negative 0.5 t. You should remember about negative exponents that it really means 1 over e to the 0.5 t. So as you're starting out at 0, you're going to get 1 over e to the 0, right? And that e to the 0 is just 1. So at time t equals 0, that factor is just going to be a 1. And so you're going to end up with 10,000 divided by 10 over 50, 10 plus 50, which is 10,000 divided by 60. Now exponential functions do grow without bound. Sort of like in figure A, the e to the 0.5t, e to the 0.5t will grow without bound as in figure A. However, because we're dealing with e to the negative 0.5t, as that denominator grows without bound, the ratio of 1 over e to the 0.5t, the ratio will become very small. For example, when t is 100, you're going to get 1 over e to the 50th. Well, e to the 50th power is a huge number, and 1 over that is going to be almost 0. So now, when you multiply 50 times almost 0, you're going to get almost 0 again. And so you're going to wind up with 10,000 over 10 plus 0, or 10,000 over 10, which is just going to give you 1,000. So the whole function at t equals 0 would give you 10,000 over 60, whatever that comes out to be. But the whole function at 100 is going to be 10,000 over 10, which is roughly 1,000. And no matter how far you go out, if we went out to 1,000, to t equals 1,000, or t equals 10,000, t equals 100,000, we're only going to approach 1,000 more closely. So this function starts out somewhere around 167, and then as t increases, it's going to go up, but at 1,000, it's going to hit a peak there. So what we're really working with here is a graph that looks like option B, and this has a special name, and that is the logistic curve, a logistic curve or a logistic function. And you probably studied these somewhere in pre-calculus. If not, you would have hit them in Calc 2 usually, where you or Calc 1 or Calc 2, where you study exponential growth and decay. You have a special type of exponential growth which is called a logistic growth, where it goes up and then it levels off and reaches a certain peak at a limit there. So hopefully this whole idea makes some sense. It's a logistic curve. It reaches a peak and doesn't grow beyond that.